All right, now we're going to use mathematical induction to prove that n cubed minus n is divisible by 3 for all positive integers and n greater than 1. So important that you read the n greater than 1 so that you know your base case is going to have to be 2. And you also need to know what happens when we have to prove that something is divisible by another number. So what they're asking us to do is to prove that n cubed minus n is divisible by 3 for all positive integers n greater than 1. Now we need to translate that into something mathematical. So what we're saying then is that n cubed minus n must be 3 times some other number m, and m is going to be some integer, and we are interested in all integer values of n greater than 1. All right. So once we've set this up, that we say the thing we're looking for is 3 times some other number, then I can go through my proof by induction. So my first step is going to be prove that my statement is true for my base case, and in this case it's n equals 2. Okay, so I take my left hand side and I say, well, 2 cubed minus 2, that's going to be 8 minus 2, which is 6, and that's going to be 3 multiplied by 2, and that's fine because that's equals 3m, where m is equal to 2, so that's equal to my right hand side. So therefore my statement is true for n equals 2. All right, my second step in my inductive process is creating my inductive hypothesis, and that means that I'm assuming that my statement is true for n equals k. So all I'm going to do then, of course, in k is going to be a positive integer. So all I'm saying then is instead of n, I'm putting a k in. So I've got k cubed minus k is going to be 3m, and m is some integer. All right, my third statement now is that I need to prove that my statement is true for n equals k plus 1. And k is a positive integer. All right. So now, what we're looking for, let's try and make a little bit of sense. So in other words, what we're looking for is k plus 1 cubed minus k plus 1. So for every n, I'm putting in a k plus 1, must be equal to 3 times, and I'm going to choose another letter because it's not going to be m anymore, it's going to be 3 times a different number, but it still has to be an integer. All right, so let's have a look at our left hand side. So what we've got is we've got k plus 1 cubed minus k plus 1, and if I expand that, I'm going to have k cubed plus 3k squared, and you can use binomial expansion, Pascal's triangle, plus 3k plus 1 minus k minus 1, okay, and I can simplify that a little bit so that I get k cubed plus 3k squared plus 3k minus k. Now it feels like I have hit a little bit of a block. However, if I go back to my statement for n equals k, you can see that k cubed minus k is actually equal to 3m. And here I've got a k cubed and I've got a minus k. So if I rearrange this to be k cubed minus k plus my 3k squared plus 3k, this is actually already equal to 3m. Okay, so that's already a multiple or divisible by 3. And then when I look here, I've got 3 times k squared plus k. And I can take out a 3, so that becomes 3m plus k squared plus k. And what I've managed to do is show that this left-hand side is a multiple of 3, so that means it must be divisible by 3. So that's equal to 3p, and my value of p is m plus k squared plus k, and that is an integer. P is an integer because m and k are both integers. Okay, this is an important statement to write. Okay, and so I can say that's equal to my right hand side, and I'm running out of space here. Let's just shrink it a little bit. Oops. I still need to write my statement at the end. So therefore, statement is true for n equals k plus 1. And then I can say, therefore, my statement is true. Now you need to be careful. N equals 2, 3, k and k plus 1, where k is a positive integer. Therefore, by mathematical induction, my statement is true for all integers n greater than 1.